Okay, YouTube, in this video I'm going to introduce the method of completing the square and talk us through it. But essentially what I want to do is point out that in our last video we were asked to solve, say, some trinomial here, x squared plus bx, we'll say plus c equaling 0, to solve this equation. And what was really advantageous is if we could rewrite it as really a binomial square equals some, maybe 0, maybe some constant, but once we get it into this form, it's really kind of nice because we can just take the square root of both sides and use square roots to solve this. So our main goal in this video is going to be to learn how can I take some trinomial in standard form, this ax squared plus bx plus c form, where in this case specifically a is equal to 1. But we say rewrite it in this square binomial form so that we can get a constant on the right and something squared on the left and use square roots. What we're going to need to do is make sure that this thing on the left really is what we call a perfect square trinomial. And so what we'll do is, if it's not a perfect square trinomial, learn to what we call complete the square. So in words, let's take a look at this. We say to complete the square for the expression x squared plus bx, what we're going to do is we're going to add b halves squared to the expression. Okay. But in diagrams now, let's take a look at what this says essentially in words. According to what we've said in words up here, as long as we add this c value here, we would say that x squared plus bx, if we were to add this on, half of b squared, then we would have what we call a perfect square trinomial. And the reason why is because we see down here it says in each diagram the combined area of the shaded regions is x squared plus bx. So far we haven't added on this b halves squared part to it yet to make it a perfect square. But you'll see here we have some x squared, which is our x squared part of this expression here, x squared, right there. And so we'd say x times x is this x squared area. And then we're adding on b times x, where we're saying b is just this length here, and x is still the same width that we had on the square here. So it's a b by x area. Essentially what we're doing when we complete the square is we're going to say, well, if I were to take this b here and split it in half, I would split this whole green rectangle up into two sub areas, and we'll take this side part right here, and we will rearrange it so that it goes down and over. We kind of turn it and rotate it, but it would be sitting right here. And so we would say that getting rid of this part right here, we now have x squared plus half of bx plus the other half of bx is that whole bx term that you see here. The question is, what would I want to add on down here in this little corner? So I'll hop over this diagram you see over here. And basically recall that when we split this in half over here, this is still x in width, but now this is b halves in length. So b halves by x, and we would say b halves by x here. Then if we say this is b halves and this is b halves, well then by just the fact that these are rectangles, we say that this is a b halves by b halves rectangle, or in this case a square, and we'd say it's a square of area b halves. So essentially, if we were to take x squared plus bx, what we just said in words up here, which says take half of b and square it, add that on to this. What we're saying in words is in the diagram here, just filling in this last little corner down here. So what I want everybody to see is the algebra of the matter is, if you ever have an expression x squared plus bx, which we're going to have a lot, and we add on specifically half of this b value that you see here squared to it, then I guarantee you that what you get is a factored expression, which, by the way, this entire square, if you look at this here, is x plus b halves in length. And it is also, this is an x here, it is x plus b halves in width. And if we were to take x plus b halves times x plus b halves, we would get this whole square of that area. So in other words, we would say x squared plus bx. The moment we add on that last little corner down here, which is b halves squared, we get a perfect square trinomial. And not only is this a perfect square, it can be factored into the square of a binomial, which, recall, our whole goal is to rewrite a trinomial into a squared binomial form so that we can take the square root of both sides and solve with square roots. So using what we know here, what you're going to see are three expressions down here that say find the value of our c term that would make this expression a perfect square trinomial. So in terms of perfect square trinomials, let's go ahead and write this down. Perfect square trinomials. And I want to write down the scheme here. But basically we're going to keep using the fact that if we have some x squared plus bx, where I'm going to change colors here on purpose. This has to be a 1. And this middle term here, what we're going to do is we're going to change colors here. add on b halves squared to it. If this happens, then we know that we're going to get something that factors down into the square of a binomial. And not only that, the value that goes in here is that half b that we're going to square to get this c value in the first place right here. So when I say, looking down here, x squared plus this bx plus c, the first thing I'm asking is, what should we put in for c that would cause this to be a perfect square trinomial? So showing my work here, I notice that the b value is 12. So I could say x squared plus 12x, but literally I'm going to write this, plus 12 halves squared, or half of b squared. So what we really get here is x squared plus 12x, and we would say, well, half of 12 is 6, and 6 squared is 36. This would have to be a perfect square trinomial. Notice how the first term is a squared, the second term is a square of 6, and we would get 2 times x times 6 to get this middle term here. So the second directive here was then write the factored form of the expression. Because I added on half of 6 squared here, I get a perfect square trinomial. Not only that, but it has to factor into the square of a binomial, which in this case, what goes in here is always b halves. And that b halves in this case is this 12 halves that we had here. So really a positive 6 is half of positive 12. So this right here, noticing that I have this, if we would have had a perfect square trinomial like this in an equation, we could have factored into the square of a binomial and then used square roots to solve this. Let's take a look at these next two examples here. I say, well, I've got x squared plus bx here. What's our c value that would cause this to be a perfect square trinomial? So again, I would say x squared minus 16x plus now b halves squared, which I'd say our b is negative 16 and half of that is just over 2, and we say square this. So really I get x squared minus 16x, and this would have to be negative 8 squared, which a negative squared just becomes a positive, and 8 squared is 64. So here's our perfect square trinomial, and furthermore, we know it has to factor then into this special pattern, where we would say this would just be a minus 8 here, okay? And the reason why I'm getting minus 8 is because, well, it's this value right here that we squared to get that c term. Now this last example shows what happens when we have an odd b term. So we would say x squared plus 7x. What would I really want to add on to this to get this to be a perfect square trinomial? Well, I hope you're catching the drift here. It's always half of our b term squared. So I say 7 over 2 squared. And furthermore, if we simplify this, I would say when you square a fraction, you square the top and the bottom, so we get 49 fourths. So you get a lot of people that struggle with, well, what does this factor into? I mean, what should I put in here? And the bottom line is that if this is a perfect square trinomial, then you always just put half of that middle term in there, this half of b that we've obtained here. So we would say this is just a 7 over 2, and this is the factored form of this expression. So when you're completing the square, all we're really doing is taking this trinomial here and adding on a constant that would allow it to be a perfect square trinomial, and then factoring it into the square of a binomial. Cheers.